Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to talk on module Photolithography under the paper Physics at Nanoscience and Technology Part 1. So after completing this module, the students will be able to understand the historical development of photolithography, its working procedure. What is the use of exposure or printing systems in photolithography? What are photomasks? What is the resolution in projection systems? What are the light sources used in the system? And fabrication of quantum dots using photolithography. Photolithography or optical or UV lithography is a microfabrication technique employed to pattern parts of a thin film or bulk of a substrate. The desired geometrical pattern is created on a photomask. This pattern is transferred from the photomask onto a light-sensitive material, often termed as photoresist of resist on a substrate. Further chemical treatments are done to engrave the exposure patterns on the substrate. Additionally, a new material can also be used to deposit in the desired pattern under the photoresist. This technique is widely used in semiconductor industries to produce modern CMOS devices. Fundamentally, photolithography is somewhat similar to a conventional photography in the fact that the patterns or features in the resist is produced by exposing light onto it. Light can be exposed either directly or without mask or with a projected image by using the photomask. Printed circuits boards are also produced by following this method with high precision. Following steps of the process are similar to the lithography printing. This technique is extensively used owing to its ability to create extremely fine patterns of order of few nanometers in size. This technique can be used to produce objects with controlled size and shape. It is very cost effective technique to create patterns over an entire surface. The important limitation of the technique is the requirement of substrate with the flat surfaces and is not an effective process to produce curved or twisted shapes. Additionally, the process is carried out in extreme clean environments. Now let us see the historical development of photolithography. The term has Greek origin where photo means light, litho means stone, and graphy means writing. Literally, photolithography is a printing technique originally used limestone printing plates wherein light plays a very crucial role. The technique was first used in 1820s by Nice for Nicepace, who used bitumen of Judah, naturally occurring asphalt, as photoresist. A layer of bitumen over a metal or glass or stone plate became less soluble upon exposing light on it. Thus, it became difficult to remove this layer, whereas the unexposed part could be rinsed with an appropriate solvent. The substrate could be removed by suitable treatments such as etching out the metal to produce a patterned printing plate. However, the sensitivity of bitumen towards light is poor and very long durations of light exposure were needed. Nonetheless, since it is economic and has excellent resistance to acid attacks, it was extensively used even in early 20th century. Oscar Swiss in 1940 developed positive photoresist by diazone phythoquinone. Positive photoresist works in opposite manner to the negative one, where an originally insoluble coating became soluble after exposure to light. Louis Playback in 1954 developed dicryl polymeric letterpress plate, thereby accelerating the plate preparation process. Students, let us see the working procedure of photolithography. The photolithography involves multiple sequential steps which can be summarized as: first, cleaning. It is the first step in the photolithography process and involves removal of both organic and inorganic contaminants that might be present on the surface of the wafer. It is usually achieved by wet chemical treatments such as RCA cleaning method, which involves cleaning by the use of solution of hydrogen peroxide, that is H2O. Other solutions used to clean the wafer may include trichloroethylene, acetone or methanol. Second, preparation. The wafer is heated to about 150 degrees Celsius for about 10 minutes to remove any moisture present on the wafer surface. Previously cleaned and stored wafers must be cleaned before use. To promote adhesion of the photoresist with wafer, liquid or gaseous adhesion promoters chemicals, for example, bi-trimethylases, amine, hexamethyl disilazane, HMDS, etc., are used. In case of silicon dioxide wafers, the surface reacts with HMDs to produce trimethylated silicon dioxide. This compound is extremely repellent towards water and obscure aqueous developer solution from penetrating between the photoresist layer and the wafer surface. This presents the lifting of fine photoresist structures, thereby damaging the pattern to be developed. To avoid this, the wafer is covered and placed on a hot plate to dry at about 120 degrees Celsius. Then third, applying photoresist. Photoresist can be applied on the wafer surface by spin coating. To do this, a viscous solution of photoresist is dropped onto the wafer and the wafer is spun to produce a uniform layer of the resist on the wafer surface. Spin coating is performed at 1200 to 4800 rpm for about 30 to 60 seconds. The thickness of the developed layer typically varies from 0.5 to 2.5 micron. The uniformity achieved with spin coating is within 5 to 10 nanometers. Fluid mechanical modeling is applied to explain this uniformity in film thickness. It is found that the speed of movement of photoresist is differential through the film. It moves faster at the top and slower at the bottom. The movement of resist is restricted at the bottom due to the viscous force which bind is to the wafer surface. Therefore, the topmost layer of the photoresist is removed quickly from the wafer edges while bottom layer creeps slowly in radical directions along with the wafer. Thus, any bump or ridge of the photoresist is removed, resulting in a flat layer. Evaporation of the liquid solvent from the photoresist solution coated over the wafer surface also affects the resulting thickness of the produced films. After application of photoresist, the wafer is heated around 90 to 100 degrees Celsius to remove excess resist solvent. This is usually termed as pre-baking the wafer. Fourth, exposure and development. After pre-baking, the resist is subjected to light exposure. The exposure to light changes the solubility of the photoresist such that some part of it can be easily dissolved in developer solution analogous to the developer used in photography. In case of the positive photoresist, most commonly used type of resist, exposed parts become soluble in the developer, whereas in case of negative resist, the exposed part can be dissolved and exposed part of the resist become insoluble. The wafer with photoresist is again baked to decrease the possibility of standing waves resulting from destructive and constructive interference of the incident light. Deep ultraviolet lithography also uses a chemical amplified resist card. UV lithography is more sensitive towards post-exposure baking duration, time as well as delay, since majority of the exposure reactions such as creating acid, making the polymer solution is the basic developer occur during post-exposure baking. The developer solution is also applied via spin coater just as resist. Earlier developer solutions mostly include sodium hydroxide. Unfortunately, sodium contamination is highly undesirable in MOSFET technology as it degrades the insulating behavior of gate oxide. So, sodium ions tunnels across the gate, thereby causing changes in threshold voltage of the transistor such that it may turn on before or after the threshold. To avoid this, metallic ion-free developer solutions have been developed using trimethyl ammonium hydroxide. The wafer after putting developer is hard baked to enhance its durability during future treatments. Etching. Both wet or dry etching can be performed. Wet etching uses aqueous chemistry while dry etching uses plasma to remove the uppermost layer of the substrate from the area which is not protected by the resist. Semiconductor manufacturing uses dry etching because it can be made anisotropic, thereby avoiding considerable undercutting of the photoresist patterns. It assumes great significance when the width of the pattern or feature is comparable to the thickness of the material being etched. Wet etching is usually isotropic and is highly desirable in microelectromechanical systems wherein suspended features are to be released from underlying layer. The development of anisotropic load defect dry etching has allowed developing very fine features in resist via photolithography, which can be easily transferred to the desired surface. Next is the photoresist removal. An aqueous resist stripper can alter the resist such that it does not adhere to the surface anymore. Another technique to remove the resist is by oxygen plasma treatment, which oxidizes the resist. This process is known as ashing and is similar to dry etching. Alternatively, 1-methyl-2-pyrrolidine NMP can be used to dissolve the photoresist. After dissolving the resist, the solvent can be removed by heating at 80 degrees Celsius. Now students, let us see the exposure or the printing system. Exposure system produces an image on the wafer by using photomask. A photomask selectively allows the passage of light from some areas and blocks it in the rest of the areas. Alternatively, maskless lithography can also be used wherein a precise beam is directly focused onto the wafer without masking it. However, this technique is not a common practice in commercial applications. Exposure systems can be classified with respect to the optics used to transfer the image from the mask to wafer, and these are contact and approximity systems. These are the simplest type of exposure systems. In case of contact system, the photomask actually touches the wafer and the uniform light it exposed on it. In proximity system, there is a small distance between the mask and the wafer. Both the system's entire wafer is covered by the photomask and the pattern is created simultaneously on each. Both techniques require illumination of the wafer with uniform light intensity. The mask should be precisely aligned to the feature present on the wafer. With increasing dimensions of the wafer in today's technology, the use of these techniques has become difficult. Contact type systems may cause damage to the photomask as well as wafer. Due to this reason, this technique is not used at commercial scale. However, owing to the economic equipment and high optical resolutions, these techniques are still used in research and prototype processes. Resolution achieved in proximity system is close to the square root of the product of wavelength and gap distance. Since the gap distance is approximately zero, the resolution achieved in proximity lithography are comparable to the more advanced lithography techniques called projection. Because of the low cost involved in installation of the systems, these systems can be used in nano imprint lithography. Projection systems. Projection systems are extensively used in VLSI technology as lithography technique. In this technique, only one die or an array of dies are exposed to light by using projection mask. The mask is projected on the wafer several times to produce the entire pattern. Now let us study about the photomask. A computerized data file is used to create the image of the mask. The computerized file can be produced byLedit, Layout Editor, Cleven, etc. softwares. This data file is converted into a series of polygons, which are then written on a square-shaped fused quartz substrate covered with the layer of chromium used as a photolithographic process. A beam of laser writer or electrons or e-beam writer can be employed to expose the pattern produced by data file. The beam is then moved over the substrate surface in either a vector or a raster scan manner. Where the photoresist on the mask is exposed, the chrome can be etched away, leaving a clear path for illumination light in the stepper or scanner system to travel through. Resolution in projection systems. The resolution of these systems is limited by the wavelength of the light used as well as the ability of the reduction lens systems to capture enough diffraction orders from the illuminated photomask. Present photolithography equipment employ deep ultraviolet light from excimer lasers having wavelength of 248 and 193 nanometers. Thus, the minimum feature sizes can be reached up to 50 nanometers. Excimer laser based lithography technology is termed as excimer laser lithography. Owing to the possibility of achieving higher resolutions, excimer laser lithography has played a significant role in the continued advancements of so-called Moore's law from past 2 decades. Minimum printable feature size by using a projection system can be expressed as CD equals to K1 into lambda by NA, where CD is the minimum feature size or known as critical dimension. K1 is a coefficient accounting for processing factors and its typical value is equals to zero point 0.4 for manufacturing. The feature size in projection lithography can be decreased by reducing K1, which in turn can be tuned by computational lithography. Lambda is wavelength of the light, Na is the numerical aperture of the lens. From the above relation, reducing the wavelength of the light used in an effective alternative to decrease the feature size. Additionally, the numerical aperture can be increased to obtain a tightly focused beam and a smaller spot size, thereby further reducing the feature size. Nonetheless, these designs methods are further retained by another parameters known as depth of focus df, which can be expressed as df equals to k2 into lambda by na square, where k2 is another coefficient depending upon the process, the thickness of resist and the topography of the wafer. Both are restricted by depth of focus. The topography of the wafer can be flattened via polishing prior to high resolution lithography steps. Light sources. The earliest photolithography experiments employed UV light from mercury-based discharge lamps, which also used a combination of mercury with noble gases like xenon. Such lamps emit light with a broad spectrum with a significant peak in UV range. This spectrum could be filtered to obtain individual spectral lines. Mercury lamps used in lithography exhibit spectral lines at different positions. These are 436 nanometers, 405 nanometers and 365 nanometers. However, with the advancement in semiconductor industry, high resolution is required to fabricate denser and faster chips. Additionally, the throughput must be higher, that is, cost-effective designing techniques. The mercury lamp-based photolithography could not meet these demands. The problem was resolved by Kanti Jain while working at IBM in 1982 when he used excimer laser lithography to obtain higher resolutions. This technology has now been extensively used in the production of microelectronics. Krypton fluoride 248 nanometer and argon fluoride 193 nanometer lasers are the most commonly used lasers in deep UV excimer lasers. Since the excimer lasers work with a certain gas mixtures, thus vary the wavelength is not trivial. As the method of generating the new wavelength is completely different and the absorption characteristics of the materials changes, feature size of as low as 50 nanometer can be obtained in optical lithography by using argon fluoride excimer laser and liquid immersion methods. This is also called as immersion lithography and allows using optics with NAS above unity. Ultra-pure deionized water is generally used, which results in a refractive index higher than air between the lens and the wafer. The water is continuously circulated to avoid thermal induced distortions. While using wafers, NAs of 1.4 can be obtained. To further increase the numerical aperture, fluids having higher refractive index must be used. Using liquid immersion lithography, the feature size can be reached up to 65 nanometers. These days, high-index immersion lithography is being used to achieve further high resolutions. For instance, IBM has recently demonstrated feature size of as low as 30 nanometers. Certain lasers can be employed for indirect generation of non-coherent extreme ultraviolet light having 13.5 nanometer wavelength for use in extreme UV lithography. Additionally, visible and infrared lasers have also been demonstrated for use in lithography. In these cases, photochemical reactions occur due to multi-photon absorptions. The use of these light sources has applications in creating true 3D objects and process non-photosynthesized glass-like materials with excellent optical resiliency. Now let us see the fabrication of quantum dots using photolithography. Quantum dots are produced by photolithography method. However, these quantum dots have been reported to have dimensions more than 10 nanometers, and the production of every similar quantum dot is difficult to achieve even with high frequency UV light. Therefore, electron beam lithography is used for the synthesis of quantum dots. In this approach, a highly focused electron beam is scanned to produce desired patterns onto the surface of the substrate. The substrate is usually coated with an electron-sensitive film termed as resist. The resist material normally consists of a polymeric compound. If the resist contains of a long chain polymer with high molecular weight, it is called as negative tone, whereas short-chain polymeric resists are known as positive tones. In case of negative tone, resist exposure to electron beam induces further polymerization of the chain length, but for positive resist, a reduction in the chain length occurs. The electron beam alters the solubility of the resist, thereby allowing selective removal of either the exposed or unexposed regions of the resist by immersing in the developer solvent. The purpose is to create very small structure in the resist that can subsequently be transferred to the substrate material, often by etching. The resolution of this electron beam process not only depends on the minimum width of the source electron beam, but it also depends on the development process. The source of electron beams are usually hot lanthanum hexaboride for lower resolution systems, whereas higher resolution instruments uses field electron emission sources such as heated tungsten zirconium oxide for lower energy spread and enhanced brightness. The advantage of electron beam lithography include high degree of flexibility for design nanostructure systems such as quantum dots, wires or rings with resolutions below 10 nanometer. However, the spiral resolution needed to be observed significant quantization effect is much higher. Additionally, a new form of lithography called Imprint lithography is best suited to produce quantum dots. Instead of etching a semiconductor wafer with light, a negative image is formed on a hard silicon dioxide wafer using electron beam lithography. This mold is used as stamp and is physically pressed onto a silicon layer to form the quantum dots. This technique allows precise positioning and the size control of the quantum dots and is being investigated for use in classical and quantum computing applications. Lithographic methods and subsequent processing often produce contamination, defect formation, size non-uniformity, poor interface quality, and even damage to the bulk of the crystal itself. So students, let us now summarize what we have learned in this module. We have seen the historical development of photolithography, the working principle of photolithography, and the important parts of photolithography like exposure and printing systems, photomask, resolution and projection system, light source in the system, and finally, we have also seen how the quantum dots are fabricated using photolithography. Thank you.